So thank you for inviting me today to be here. I want to give you a little bit of a timeline on the work I'm going to be talking about and sort of the origins and the current work. I'd like to start with the 1930s and a pretty remarkable piece of work that Nikolai Bernstein put together at the time, pretty much our first motion capture system. And I want to just show you what he was doing back
снимков в минуту. Специальный аппарат фиксирует все фазы движения мастера. Каждая фаза движения детально изучается.
I thought that was pretty impressive, and he figured out how to collect motion data at 200 hertz at the time, and so he gained a pretty good insight into both the abundant degrees of freedom that the human body has and the amount of variability that it actually generates when it repeats the same motion. And so by 1966, after he passed away, this was in the Soviet Union, so things were not really flowing back and forth between the US and Russia. So his work was translated to English, and we essentially began the field of motor control around sometime later when a lot of the former students of his migrated to Canada and the US. So by the 1980s, there was quite a bit of work here at MIT on trying to model trajectory formation on planar motions and trying to model or uncover motor primitives. In the work of Bitsy and Emil Hogan put together a model to try and tackle the trajectory generation problem. So around 1995, I started graduate school, and my advisor, David Zipser, asked me to try to tackle that problem of redundancy, meaning that we have many more degrees of freedom in our body than the dimensions that we have in the space where we conceive goals and tasks and constraints and contextual situations. And he asked me, how would you address this problem? So I went on and learned about what the world had done up until then, model it, and then kind of research its origin. So I noticed in particular that they were using a framework called optima control. And in that framework, you define a cost functional that depends on time. And so when you find the trajectories of the motion that you're trying to model, you are finding not only the path to travel to a particular goal or target, but you're also trying to resolve the time that it takes to complete that and the temporal profiles that it takes to complete that trajectory. So when you solve this integral over time, you actually have a prescription of the amount of time that it must take to move. So say 800 milliseconds, and you have to solve the trajectory not only for the path, but also for the amount of time that it's going to take you, and also for the profile that you're going to travel along that path. Now, as a graduate student, I thought that was a very complicated thing to do. But why was it done that way in the field, in the engineering field that they were trying, and what kind of problem were they trying to solve was different from the problem I thought that we had ahead in front of us. And so essentially the optimization of something time dependent and minimizing time was essential because you had to go to the moon and back and send a spacecraft in optimal time to conserve fuel consumption and come back to the Earth on time. So that was a very different problem than I thought a baby trying to learn how to move would have to solve. And in particular, it was a problem because it just enlarged the space of the search space quite a bit, because you have to then do not only do time, the estimation of the path, but also the estimation of the temporal profile. So that makes the problem highly intractable. And you enter into this course of dimensionality. So I turned then, instead of looking at this field that was actually not addressing the problem of degrees of freedom, because it was modeling a planar arm moving on a two-dimensional plane with 2 degrees of freedom only. So there was no redundancy, so I couldn't really look at that for what I was interested in. So I went and looked at the work of Esther Telen, who was a developmental psychologist who actually figured out that the whole development problem was approached the wrong way. And she brought up, it was approached in a very static way, in a very linear way, using models that were inappropriate to capture what babies do and how they explore and so on. So what you got was this, she brought into the field a nonlinear complex dynamical systems approach, and completely revolutionized in the 80s what psychologists were doing in studying development. Then by the 1990s, there were two developments in the field of motor control that caught my attention because of the problem I was trying to solve. One was the uncontrolled manifold concept, which addresses the problem of variability, and for the first time begins to think about different types of variability that could define task-relevant dimensions in any given context versus task, they call it task-irrelevant dimensions. And later I sort of began to understand that it's actually a task incidental dimensions that support and provide a lot of the adaptive learning that we see in adaptive motor control. The second piece of work there was by Harrison Wolpert, and it was a paper that really turned the field into a different direction, where we started to try to understand at different layers of the nervous system the noise, the concept of noise in the signal and the noise-to-signal ratio. By 2001, I had completed my PhD thesis and had provided a series of geometric solutions to this problem, where I had decomposed the problem into the past generation, the problem of trajectory formation in general, into a past generation that was geometrically optimal with respect to the distance metric of the spaces involved, the internal configuration space and the space of the end effector. And I had provided empirical data supporting the notion that this separability exists at least for goal-directed behavior in movements that are deliberate, that are staged, and that have a particular purpose. And so by 2012, I have become very curious about complex motions performed by artists, performing artists, ballet dancers, and modern dancers, and by particularly by athletes, by high-performance athletes. And around that time, I discovered a new class of movements, which I coined spontaneous or consequential, because they were not instructed and they were not guided by a particular goal directly. But most importantly, what these movements demonstrated empirically was that there was a direct dependence on the dynamics, unlike the goal-directed movements that were deliberate and were dynamic invariant. And so in this case, the geometry of the path actually changed with the demands of the dynamics, unlike the movements that are cognitively controlled. And And that gave me an opportunity to begin thinking about different classes of taxonomy of different classes, of different layers of biorhythmic activity, from autonomic, from somatic, and from central nervous systems. And I began to explore in thousands of individuals the signatures, the stochastic signatures of these motions, with the purpose of creating a new platform to revolutionize clinical applications, to actually translate all the clinical tests that we have into a new framework for precision medicine, a new platform that other people have developed to form a personalized, targeted treatment in cancer research. But in psychiatry, then I thought there is an opportunity to utilize this framework and redefine the way that we study behavior. So I'm going to now walk you a little bit through the modeling that I did earlier on, based on the problem of the Bernstein degrees of freedom problem. And the problem illustrated here with a toy model of an arm that has 7 degrees of freedom. So these are 1, 2, 3, 4, 5, 6, and 7. So that's a subset of the degrees of freedom that an arm has. And the problem is that you have a many-to-one map from many configurations, possible configurations. I'm illustrating just 3 configurations here that map to the same end effector. And the question that Bernstein asked was, how come we have a systematic solution and a solution that is consistent all the time, when in fact, because we have over 600 degrees of freedom across the body, we could actually perform a trajectory in many different ways. So how do we do that? So, the problem is then, how do you, given an n effector, how do you find the inverse map?
So is the problem, how do you find a solution, or how do you find the best solution?
A solution, because there's never a best solution overall. There is a best solution for every context or every task.
But then if there are many solutions, why is it difficult to find a solution?
Because the smoothness of the path is important, and you would not have that if you at every time step recruited arbitrarily a degree of freedom. So there is a connectivity there that emerges non-trivially. So I propose to then conceive this problem geometrically and uncover a way to generate the paths along 2 manifolds that would be representing the internal configurations of space that give rise to different postures of the body, and the n effector space where we define goals and we could define constraints and the context. And so what I did was then build an embedding. This is called a locally linear isometric embedding. And what you do is you define the geometry of the smaller dimensional space, and you embed in the higher dimensional space, preserving the metric. This is called a pullback, where you compose the map. First you define a forward map, and then you compose that map with the internal configuration space, and so you pull it back, and when you measure the distances in the space where you're actually planning the motion, you're also then measuring the distances in the internal configuration space. And this is the differential that I built. It is a gradient, but it's not just any gradient like in common gradient descent. It's a contravariant gradient. It uses the natural gradient of the space of tasks and configurations that you define. And that comes from considering the metric, the distance metric, the norm that you have in the space where you define your goals and your tasks, and combining it with a Jacobian, which is the derivative, the matrix of derivative of your coordinates, and then bringing it to the configuration space. So you are bringing back the geometry of the external space, where you can define any kinds of, so you can define any task or any goals as a general, and then you bring that back into the internal configuration space, and you bring that, now you bring that metric. What this gives you is the ability to model many different tasks and recruit dimensions. So it's not that we have redundant dimensions. We actually the brain can recruit degrees of freedom as needed on demand, depending on the task. And you can then change the geometry of the space where you define your task and your context. And that has an impact in changing the geometry of the internal configuration space.
And you're thinking about all this in a deterministic setting rather than in a noisy setting?
So yeah, so the initial solution to do this was deterministic because it's a very complex problem. So the initial question was, how do we do this in such a way that we define the optimal path for a given set of conditions? So that would be the geodesic to travel from point A to point B. The unique solution would be geometric, in the sense it's the shortest for that particular space. Then, as you will see the evolution.
What you were asking before? I mean, what?
Sorry?
Optimal in the sense of minimizing time?
Distance. Distance. Remember, I have decoupled time from space here. Right, and it will become more obvious in the next slides. But essentially, once you do this, you can decompose that high-dimensional space into the dimensions that are relevant to the task, much like the uncontrolled manifold people did, but in this case I did it with the appropriate geometry. And so the other dimensions are flowing there, and these are then enable you to study two different types of variability in goal-directed behavior. Then you switch to the stochastic approach. And then you can do this while considering the variability of the system. Yeah. I think that I would like to move so that I can, it's a lot to cover because then I get into the stochastic model. But I will take all your questions afterwards. So now we have a situation where we have 3 degrees of freedom defined by the position of the target, for example. And then that will recruit 3 of the degrees of freedom in that embedding. So you are navigating in 3 degrees of freedom in the internal configuration in space that is defined by the 3 dimensions of that external space. Now you can add another dimension because say that you want to grasp, not just point, but grasp. And now the problem is that you have to match the orientation of your hand appropriately to the orientation of your cup. Otherwise, you won't be able to grasp it. So that recruits another dimension. Now let's say that you are opening the door of your and you're carrying a bag, so you're constraining the plane of the arm. So you can also model that, to create torque. So all these different geometries, these are just toy examples, can then be modeled and can then reveal the degrees of freedom that are relevant to that task, but also the variability of the degrees of freedom that are floating, that are kind of supporting the other task-relevant space. And you can then recruit for 4, for 5, and so on. And what I like people to think about this, because these are studies that are just don't center on a person, but most of what we do is social. And so we can bring this to the social domain by now recruiting the degrees of freedom that the other person has as well when you train with that person in a social dance. And so, and that will be maybe later. So here the question is, how do we then, so the model decouples the generation of forces, the dynamics, which gives you the time profile of the motion from the geometry, which gives you the path. So is that actually empirically valid? So up until that point, that question had not been asked because all models were coupled. So you had, you were generating, the models of trajectory formation were generating both the temporal profile and the path. And so one way that you can do this is by varying the speed of the movement, because speed is distance traveled given in time. So you can then probe the geometry and you probe the temporal profile as well. So we designed this experiment where we would vary the initial configuration of the arm with different postures that corresponded to the same location space, so that you can kind of model that manifold of self-motion that the roboticists would call the self-motion manifold, that doesn't move your hand. It just moves in configuration space. You travel the path, but you're not traveling the path in the end effector. So, and then we would do that. We would do that with different speeds that were called at random. And again, the question was whether the path would be conserved. Now, the path was conserved. We varied all the speeds, and when we gathered all the speeds that were instructed, people were very good. This was very automatic behavior, and they were very good at differentiating the different speeds. So the speed profiles in time, and these are the amplitude of the speed in centimeters per second. And what you can see is that they traveled very similar paths. And what they also conserve here is the distance traveled to the peak velocity point over here prior to the deceleration phase to stop. And so the interesting thing is that in this case, what the system was varying was this parameter, I call it tau, which is the time to reach the peak velocity. So I then moved this out to the configuration space of the higher dimensions, and there we have four in the case of orientation matching, 4 dimensions that were recruited, because we have the position, but we also have the orientation angle. And this is actual data. So these are all the participants collapsed. And what we're plotting here is the orientation error and the position error as they reach to grasp for the cylinder. Match orientation, they didn't actually do the grasping, because that's another ball of wax with all the fingers and so on. So it's just matched, orientation matching. And so regardless of the speed, so the different speeds that we tried, there was a co-articulation of the 4 joints in that task-relevant manifold, and that's important because you could have serially solved this problem by first displacing, then rotating, then displacing, then rotating, because of the abundant degrees of freedom that we have. But what the system does is co-articulates and couples that 4-dimensional space from the rest of the other 3 dimensions in this case. And so we also, when we vary the initial posture, that invariant remained for the orientation and the position relationship, and so it did when we vary the orientation of the target. So you have to match different orientations coming from the same position and from the same postural initial configuration. And so that provided a set of invariants. And then we moved to more complex tasks where we have to actually avoid obstacles. And so this is just without obstacles. Then we started placing obstacles and making the task quite complicated. And so this is the model, but this is just the flow of the equation of the differential, and it's reaching in multiple ways and so on and so on. Now these are geodesics paths with respect to the distance metric that defines the obstacle avoidance, which is different from the distance metric that defines the orientation matching and so on. So you can accomplish this model in 2 ways. One is by conserving the metric but changing the coordinate functions that define your map, or by conserving the coordinate map and changing the metric. And they're equivalent. And so here now we are, I moved to Caltech to work with Richard Anderson and try to, this model also I used, so that the work I just spoke about is my PhD thesis, and a third of the thesis is empirical work to try and bring home that message of the coupling of force generation and the equations of motion to generate action based on a force-independent geometric solution. And the other part was artificial neural networks, because my advisor, David Zisser, was one of the people who pioneered sort of the artificial neural network framework to to uncover gain fields and so on. And so he had done work with Richard Anderson, and because the artificial neural network model made certain predictions about past generation and this geometric solution, then I moved to Caltech to learn the electrophysiology and begin to explore this decoupling of the space-time in the posterior parietal cortex, where you have all these coordinate representations and sensory motor integration and sensory motor transformation. So I went there, and the first thing was to begin to record in tandem the spike activity with the full body activity. And in this case, I could afford to do it with sensors that I placed on the animals. So these are data from rhesus macaques, and they were trained to reach straight to a target. So they were trained in the delayed reaching paradigm, where you flash a target and then they have to wait for a variable amount of time to reach the target. And during that amount of time where they're not moving, they're not performing the action, but they're thinking about it, I performed those recordings to see the extent to which the activity in the posterior parietal cortex could predict the path both in the postural configuration space of the arm and also in the hand space. And so before launching into the spike analysis and recordings, I built a model of the trajectory generation, and I tested now to see if the invariants would keep. Now, the speed invariant did keep, and it was very interesting because these animals were not trained to perform this task. They would get only the training each day that they were exposed to. And so from the first time, they have resolved the path length, okay, the entire path and the path curvature. And what they were actually exploring was the distance traveled up to the peak velocity point over here, which corresponds to these dots. So these are the speed profiles corresponding to this path. The blue ones are corresponding to the learning phase. And after a few trials, they would adapt, and they would actually consistently travel the same distance, much like in the other experiments that I showed you with the humans and the orientation matching. So now you have a consistent distance traveled up to the point of peak velocity. But all along, all these points were reached at the same time. So whereas this result here gave me evidence that, in fact, it would be very inefficient to try and model this using the optimal control framework, because there is this time coupling in that model, but each trajectory is different here in time. So you have not only a different duration of the integral, you also have a different altogether travel profile along that path. This path can be modeled as geodesics, so these are geodesics in some space, and these are the time to reach that peak, and eventually then they all converge to the same kind of distance travel. And this is just for one target. Obviously, I mapped out the entire space of the reach. So there are different asymmetries there that you have to consider, and so I mapped the entire time space, and then I was able to show systematically the deformations that map of time across space suffers when you put an obstacle. So you can model the geometry of that times of that, and estimate time from space essentially by figuring out the proper distance metric that will give you the consistent path duration. Now, in the process of doing that, I realized there is a symmetry here that emerges, which is the area constrained between two different geodesic curves. And so this was a prediction of the model. When you do geodesic hopping from one geometry to another, there is a conservation. And so the example here produces the Euclidean geodesic between these 2 points, and also the geodesic corresponding to the model of the obstacle avoidance. And the point of maximal curvature around that path defines this region here, and the area in this region, the ratio given by the area in this region divided by the total area is 1/2, and the perimeter here is also divided by the total perimeter is 1/2. Now that's the prediction of the model. So the question was, how does this hold water in the actual empirical data? And turns out Turns out it does. So this is the very dramatic differences across the space when you put these obstacles.